This video is going to be focusing on a small section of topic 19 of the A2 chemistry course for Edexcel. We're going to be looking at amines. So we're going to be discussing the nomenclature and how to draw amines. We'll be looking at the reactions of specifically primary aliphatic amines and some aromatics with water, acids, halogenoalkanes and copper. We'll also be looking at their miscibility with water and the reasons for their difference in basicity. We'll be looking at the preparation of these aliphatic amines, as well as the preparation of aromatic amines, and the reaction of aromatic amines with nitrous acid in order to form benzene diazonium ions, and how we can then form a dye from that. And lastly, we'll finish off with some past paper questions. So first of all, we're going to look at what is an amine. Well, an amine is an organic compound that contains the functional group NH2. And similar to our alcohols and our halogenoalkanes, they can be classed as primary, secondary, or tertiary, depending on the number of alkyl constituent groups. Now, I'm sure that you know this already, but just as a quick reminder, primary are going to have one alkyl constituent group, secondary are going to have two, and tertiary are going to have three. Now, most of our focus is going to be on primary amines, but we may also talk about secondary or tertiary when we're looking at additional reactions as a side product. Now, amines do occur very widely in nature, and they are actually used in many drugs, both legal and illegal, but we're going to be looking at more to do with the chemistry of how they react. So let's first of all look at the structure of some amines. Well, we have four aliphatic amines. We have methyl, ethyl, propyl, and butyl amine. And of course, because we've been studying the aromatics, we're going to add in an aromatic amine, which is phenylamine. And of course, you can see that it's got the benzene ring here. We do need to know that they are a gas when we've got methyl and ethyl. And as we increase our hydrocarbon chain, we're going to form liquids, and we're going to talk a little bit about why we have liquids and why we have miscibility later on in this PowerPoint. Now, aliphatic amines can be prepared in a number of different ways. The first way is by reducing a nitrile group using LiAlH4 in dry ether, and this is the equation for that. Remember that we just write H for our reducing agent. We don't need to write it out in full because it is just how it is reacting. Similar to when we have oxidation, we just simply write O in the square brackets. Another method involves heating a halogenoalkane with ammonia, either under pressure in a sealed container, or we can use concentrated aqueous ammonia. Of course, we need to have the sealed container because ammonia is a gas and we do not want it to escape. Now, the reaction for this, you can see here we've got chloromethane reacting with ammonia to give us our methylamine and a hydrogen chloride. And this involves a nucleophilic attack by the lone pair of electrons, and we have that lone pair shown on the ammonia. And our carbon within our halogenoalkane is electron deficient because we do have that difference in electronegativity between the carbon and the chlorine. You'll have covered that back in topic 10 in AS. If you can't quite remember, feel free to have a look at the video that is posted on the YouTube channel. So the product that's formed in this first step, where we've got here our primary amine, this also contains a lone pair on the nitrogen. So we're going to form this product, and it contains a lone pair on the nitrogen. The biggest issue with this particular reaction is that this lone pair can also act as a nucleophile, and it starts to compete with the ammonia in order to attack the halogenoalkane. Now, we don't want that. We want to be making only the primary amine, because if we allow this attack to occur, then we're going to make a secondary amine, and we can see that here. So what we do to avoid this unwanted secondary amine is we use a very large excess of ammonia. This allows us to ensure that there is no competition for the reactants by the primary amine, and the only thing that is going to be attacking, and the only nucleophile that's going to be attacking the halogenoalkane is the ammonia. So we want to completely outnumber it. Now, some of the excess ammonia can also react with the hydrogen chloride, and we're going to form ammonium chloride. Now, you do not need to know the mechanism for this, but it can be helpful for you to see how this reaction actually happens. So what we have is we start off with our chloromethane, as we can see here. And we know that this is going to be slightly positive and slightly negative because it has an electron deficiency. We then have ammonia, which contains a lone pair, and this lone pair is going to attack the carbon that is electron deficient, and it is then going to remove the chlorine and it's going to take its place. We end up with a molecule that looks a little bit like this. Now, the problem with this is we do not want that positive charge. We want to form our primary amine, and we do have our ammonia in excess. So what happens is the ammonia, again, acts as a nucleophile, and it attacks this hydrogen, and the hydrogen is then removed to form your primary amine, as well as NH4 and Cl-. So we end up with an ammonium chloride salt being formed. Now, as I said, you don't need to know the mechanism for this, but it does make it a little bit easier if you can follow to see how this actually happens. What you do need to know is this equation here. You need to be able to write the equation to show the formation of our primary amine. We can prepare aromatic amines, such as phenylamine, when we can undergo the reduction of nitrobenzene under reflux. So the reducing agent that is used in this reaction is tin, and it is mixed in with concentrated hydrochloric acid in a round bottom flask, as you can see here, and we're going to then heat it using a condenser. So we're going to be heating it under reflux. The tin is then oxidized from tin 2 to tin 4, and the hydrogen that is produced in this particular reaction and hydrogen is produced in this reaction with the acid, and these two reactions cause the nitrobenzene in order to be reduced. Now, you do not need to know too much about how this happens. Again, you don't need to know any mechanism, but it is good to be able to see the equation. So we have our nitrobenzene here, and it is reacting with our reducing agent. Remember, we simply write this as H, and we're going to form our phenylamine, and of course we're going to make water. Now, the phenylamine is a basic substance, so given the fact that we do have concentrated hydrochloric acid in there, unfortunately we can get a neutralization happening. But we do not, of course, want this. We want to just form our phenylamine rather than our phenylammonium ion, but we can easily convert this back to the phenylamine simply by adding hydroxide ions, and we make more water, and again, our desired product. Now, phenylamine is very commonly used as a dye, and we use it for clothing, and we can also use it within polymer and pharmaceutical manufacturing. Now, with regards to the reaction of amines with water, the reaction will vary depending on the length of the hydrocarbon chain. When we have a short chain primary aliphatic amine, we're going to have very soluble substances in water. And this is because they're going to form hydrogen bonds with the water molecules. We already know all about hydrogen bonds and how they affect the solubility. You learned that back in topic 7 of year 12. Again, if you're not sure, remember to go back and have a look in the textbook or have a look in your notes from last year. The biggest issue is once the hydrocarbon chain gets longer, our hydrogen bonds are no longer the predominant force. Our predominant force becomes our London forces. And due to the increase in the London forces, their solubility in water decreases. Now, phenylamine is slightly soluble in water because it does have the hydrogen bonds. However, it does have London forces as well. Now, the London forces are not particularly large, so it does still allow it to be soluble in water. However, if it was any larger, it would no longer be soluble. So it's right on the border of its solubility because we do get a nice balance between our London forces and our hydrogen bonds. We can also react amines with water in order to form alkaline solutions, exactly the same way as ammonia does. And the reason that we can do this is because both ammonia and the primary amine have got a lone pair on the nitrogen. So we can react that lone pair with the hydrogen from water, forming this dative bond that we see in our CH3NH3 or NH4. And then we form our hydroxide ion. So of course we're going to be getting an alkaline solution there. And we call this CH3NH3 plus is known as our phenylammonium ion, which is analogous to our ammonium when we react ammonia. So we can look at the basicity, or how basic something is, by using the pKb value. Now, you have looked previously at pKa, and that told you how acidic something is. This works very much in the same way. The only difference is, instead of looking at acidity, we're looking at basicity. So the pKb of water at 298 Kelvin is going to be 7. That's exactly the same as the pKa of water at 298 Kelvin. If we have a value that is lower than 7, it tells us that it has a greater basicity than water. That just means if it's lower than 7, it is more basic than water. So when we look at our amines and we compare it to ammonia, we can see that ammonia, NH3, has got a pKb of 4.75. So that means it is more basic than water, but it's kind of in the middle. As we increase our hydrocarbon chain, from methyl to ethyl to propyl, the hydrocarbon chain is getting longer and we get a decrease in our pKb value. That means that we are getting more basic as we add in our hydrocarbons. So as we make the chain longer, we're going to become more basic. Now, the one that is a slight anomaly to this is phenylamine. Phenylamine actually has a pKb of 9.38, which means it is less basic than water. So we have to understand the reasons why increasing the hydrocarbon chain causes more basicity, and it is to do with the electron density on the nitrogen atom. So methylamine is a stronger base than ammonia because of the hydrocarbon chain. Basically what the hydrocarbon chain does, as you can see from the diagrams at the bottom, is it pushes the electron density towards the nitrogen. And the longer this hydrocarbon chain, the larger the push. And you can see that we're displaying that by showing that our delta negative is getting larger and larger as we go from methyl to ethyl to propyl. And we call this electron releasing. As the electrons are being released from the methyl groups, it's causing the electron density to be moving onto the nitrogen atom, which causes it to become more and more basic. Phenylamine, the phenyl group, is not a particularly electron releasing structure. Therefore, it is not going to be as basic. And we're going to look at why it is not an electron releasing structure. Just to remind you of the structure of phenylamine, it is going to look like this. And it's actually similar to a structure that you have seen before, and that structure would be for phenol. If you remember back to topic 18, we discussed about how the lone pairs in the oxygen and phenol join in with the delocalization and the carbon ring structure, and phenylamine is very much the same. One of the lone pairs, the lone pair on the nitrogen is incorporated into the delocalized benzene ring, and that delocalization allows the ring to then extend out to above and below the nitrogen. This causes the nitrogen to be actually less electron rich because its lone pair that would normally sit here is actually being put into this delocalization at the top and the bottom. So it's being pulled away. So that is less likely to form a dative bond with the hydrogen of the water molecule. In comparison, if we go back to our methyl, ethyl, and propyl, where the where the lone pairs are actually becoming more and more attractive to being able to have that dative bond with hydrogen. So it is all to do with the position of the electron density. Despite the varying basicity of amines, so despite some of them being much more basic than others, they will all react with strong acids to form ionic salts. And they will make this form of ammonium ion that will have the alkyl group at the start. So methyl ammonium, butyl ammonium, or phenyl ammonium. All of these will be able to react and form these salts. Amines can also react with ethanol chloride or our acyl chlorides. If you can't remember what that is, again, if you're not sure, go back and have a look at topic 15, where we did cover this last term. So when these react, we get two molecules joining together, and then we get a small molecule being eliminated. So we actually call this an addition-elimination reaction. And we're going to form this amide group. And this amide group here is CONH. Now we're going to talk a little bit about amides later on in another video, so I'm not going to go into too much detail, just to make you aware that the most common amide is ethanamide. And basically what we're doing is we are replacing one of the hydrogens on the NH2 group with a butyl group. You can see here that rather than us having a hydrogen here, we're removing that and we're replacing it with this butyl group. But we'll talk more about amides later on. Paracetamol is a molecule that can be synthesized using an addition-elimination reaction, and it is actually an amide. And we name it because we have para, which means we have the two groups on the benzene ring being on opposite sides of each other. Acetam is the previous name for ethanamide, and the all tells us that we have a hydroxyl group. So we have this hydroxyl group. So we have paracetamol. Again, we don't need to go into too much detail about that, but just to be aware that we can make that. Now, amines can also react with halogenoalkanes due to the presence of this electron-deficient carbon on the halogenoalkane and the electron-rich nitrogen on the amine. So that's what we've discussed previously when we were looking at the ammonia, where we can make this secondary amine. So we have the lone pair on the NH2 reacting with the electron-deficient carbon, and we're going to form this secondary amine and a hydrogen halide reaction, and a hydrogen halide is our other product. So just to draw out what it looks like, we have our phenylamine that contains this lone pair, and it's reacting with our chloroethane and our going to have a delta negative and a delta positive. So this is going to attack the carbon, and we're going to get a movement of electrons into the chlorine. And again, similar to the reaction with the ammonia, we're going to get that additional attack, and we're going to end up forming an overall product that will look something like this. Again, you don't need to know the mechanism of this, just how to draw out the structures of what we form. And this one would be our secondary amine. And we can see that because it is connected to two alkyl groups. We can also do this with butylamine and chloroethane, and again, we form the secondary amine as well as our hydrogen halide. The issue with this is very similar to the reaction with the primary amines, is the fact that this secondary amine still contains this electron-rich nitrogen, so it can actually further react with the chloroethane using this lone pair to form this tertiary amine. And we can see that because we have got three alkyl groups. Now again, this tertiary amine also contains the nitrogen that has got this electron-rich nitrogen, so it can react again with the halogenoalkane. Notice though that this time there is no hydrogen for us to be removing, so we do not make HCl as a product. Actually, what happens is we form a positively charged ion and a negatively charged ion from the chloride, and we form something called a quaternary salt. And this is essentially very similar to NH4Cl. The only difference is that these hydrogens are all replaced with different alkyl groups. And as I said, we call this a quaternary salt. Amines will react with transition metals such as copper, and are very similar as to when it reacts with ammonia. And again, it is all to do with this lone pair of the nitrogen atom. This lone pair opens up amines to a large number of reactions. When they first react with butylamine, we're going to form a pale blue precipitate. And as we add excess, that precipitate is going to dissolve, and we're going to form a deep blue solution. This is very much the same as what you've seen with ammonia. The only difference is that the ligands will change from being ammonia to being the butyl ligands, or the butylamine ligand, sorry. So it's just very much the same. Again, if you're not sure about that, go back and have a look at topic 17 and have a look at how copper reacts with ammonia. So now we need to look at how we can react this phenylamine with nitrous acid. Now, nitrous acid is HNO2 as opposed to nitric acid, which we've seen as HNO3. And we can prepare this in situ by mixing ice-cold solutions of sodium nitrite and dilute hydrochloric acid. If we then add these two things to phenylamine, we're going to form this very special ion that is known as a benzene diazonium ion. Now, the reaction vessel has to be kept below 5 degrees Celsius, or else we're going to form phenol instead of the benzene diazonium, and we actually want to form this ion. And because they carry this positive charge, they can act as electrophiles, so they will react very readily in a cold alkaline solution with any aromatic phenols or any amines, because they are an electrophile. They've got this positive charge. When they react with this, we're going to form something similar to this structure down here, which is 4-hydroxyphenylazobenzene. Okay, and you can see that you do not need to know the mechanism. You simply have to know the process. So we have this benzene diazonium ion reacting with this phenoxide ion, and we're going to form this azo structure. Now, we call this a coupling reaction, and the compound that we form, this compound here, is what's known as an azo dye, and it is very energetically stable. It has a yellow colour, and as I said, it is called an azo dye. And the reason that it is extremely stable is due to the extensive delocalization of the electrons, and the delocalization occurs because we get an alternating system all the way through the benzene ring, the nitrogen double bond, back to the benzene ring. We get an alternating system of single and double bonds. And this alternating system is known as a conjugated system. When we get this conjugated system and we get this alternating, it gives it a lot of stability because we get constant delocalization of our electrons, and it also allows an absorption of light to take place, so we get a coloured compound, and in this case we get a very bright yellow colour. So because azo dyes are very stable, they're always going to be absorbing this light, so actually they do not fade in colour. And a key example of an azo dye that you've actually come across is in the indicator methyl orange. So you can see that we have this section in the centre where we have our benzene ring with our nitrogen double bond with the benzene ring on the other side. Now remember, this is drawing it like Kekule structure, and really we shouldn't draw it like that. We should obviously draw it with a delocalization instead. So let's have a look at some past paper questions on amides. We're looking at the January 2015 paper. Now this is a synoptic section, so this is from section C. So remember, it can contain a large number of different topics, but we're quite lucky here that it's going to contain the majority of our organic nitrogen chemistry. Now, of course, when you're in the exam, you will skim read at least the paragraphs so that you can see what information that you've been given, because sometimes the information that you need to answer the question is in these paragraphs. So I cannot stress enough how important it is to make sure that you do read through it and you do refer back to it as you go through your answers. So we're looking to start off by comparing methylamine, which boils at 267 Kelvin and it dissolves in water to form an alkaline solution, and we're going to compare that to ammonia. So let's just remind ourselves of the two structures. We have methylamine versus ammonia. Now both of them, of course, contain lone pairs on the nitrogen. So we want to be able to explain why methylamine has a higher boiling temperature than ammonia. Now we do not need to give a detailed description of the forces, but it is imperative that we do discuss what forces are present. Now both of them we know can make hydrogen bonds. So there is a way to answer this question with reference to the hydrogen bonds, but actually your best way to answer this question is to look at what other bonds are there. So yes, the hydrogen bonds can have an effect, but the fact that they both have hydrogen bonds, we want to focus on the London forces. So in methylamine, it actually has stronger London forces. And the reasons for this is very simple, and it is due to the fact that methylamine has more electrons. Okay, now of course we don't need to go into the full detailed description of the forces, but we know that the more electrons they have, the more chance you have for an instantaneous dipole. That then allows for induced dipoles and so on and so on. But we don't need to go into too much detail. It is only worth 2 marks. So you get the first mark for saying that methylamine has stronger London forces, and the reason why is because it has more electrons. Now we need to be looking at why primary amines are soluble in water, but their solubility decreases as the molar mass increases. So it's a 3-mark question, so we know we're probably going to have at least 3 points here. So the first point would be to explain why primary amines are soluble in water. And the amines can form hydrogen bonds with water. That's the first and most important part. We need to understand that it can actually do that. However, as the molar mass increases, our London forces increase. And that's due to the fact that we have more electrons because we have more atoms. So your size of your hydrocarbon group is going to cause the London forces to increase. So when we get these increase in London forces, it requires more energy. To break these intermolecular bonds. And because we need more energy in order to break the intermolecular bonds, then we're not going to be able to, the enthalpy of hydration sometimes isn't enough in order to be able to break all those bonds. We don't quite have the energy that's required. Now we want to be looking at the reaction of methylamine with water in order to produce an alkaline solution. So let's write out methylamine as CH3NH2. We know that we need water and we don't need to have any state symbols here. Now this is going to be a reversible reaction because it is an equilibrium, and what happens is when it acts as a base, that's acting as a proton acceptor, and it is going to be removing the hydrogen from the water, and we're going to form CH3NH3 plus, and we're going to make a hydroxide group for 1 mark. Part 4, suggest why the dimethylamine is more basic than methylamine and why both of these are much more basic than phenylamine. Well, this is going to be split into 2 parts. So the first part is looking at why dimethylamine is more basic than the methylamine. So we're going to start off by looking at, well, what actually affects the basicity? So basicity, or the basic strength, depends on the donation of a lone pair. And it's the lone pair of electrons on the nitrogen. Methyl groups are electron donating. So the more methyl groups that you have, the more donating they're going to be. So if we have 2 methyl groups, the donation increases. And then for the third mark, we have to reference onto the phenylamine. And for the phenylamine, we have the lone pair interacting with the benzene ring. So because it interacts with the benzene ring, we get less of the donation for the lone pair, so that is going to cause the basicity to go down. So it's all to do with how much the lone pair is going to donate those electrons in order to form a dative bond with the hydrogen. So you should always be referencing that in your answers. So we have the interaction of a carbonyl group and an amine group in ethanamide can be shown in the following diagram. Now, although we haven't talked too much about ethanamide, we can still answer this question based on what we know about the lone pairs. So we just have to explain what the 2 arrows are. Well, when we have arrow number 1, which is here, this is the movement of the pi electrons to the oxygen. So we have the pi electrons and the double bond moving towards the oxygen. And arrow number 2, this one here, is the movement of the lone pair of electrons on the nitrogen to the CN bond. We can now show for part 2 the diagram that is going, a diagram that is going to show what is being formed. Well, we keep our CH3, we had no difference there, but where we had a double bond to our oxygen, well, we donated that lone pair, so that's going to look like that, whereas the lone pair from the nitrogen was donated in to make a double bond, and we're going to form a positive charge here for 1 mark. So then we have to discuss why the carbonyl group in this may not react with 2,4-DNPH. Now again, this is starting to go into a little bit to do with amides, but based on our previous knowledge, we can't actually answer this. And it is because the carbonyl in this molecule has a smaller positive charge. So the 2,4-DNPH requires a positive charge on the carbon in order for it to happen. And the carbonyl group here actually has a lower positive charge because the charge is going to be down here on the nitrogen. So it makes it resistant to nucleophilic attack. So you can have a look at the mark schemes for both of these questions that we've looked at, and you can see that everything is going to be on there. I hope this video has been useful, and I hope you've learned something from it. If you have any questions, please feel free to leave anything in a comment, and I hope to see you back on the channel to view any videos that will help you with your studying in the future.